Hello and welcome to the Movement Neuroscience Laboratory. My name is Gene Cinique. I'm a professor of physical therapy, movement, and rehabilitation sciences, and Associate Dean for Research and Innovation at the Bouvet College of Health Sciences. We'd like to thank the Cinique Foundation for investing in ALS research and sponsoring research in our laboratory. As you will see, we've built a strong collaboration with Dr. Oscar Soto, a neurologist at the Tufts University Medical Center, to develop ways of detecting ALS early in the disease process.
Hi, my name is Nathaniel Pincus, and I'm an undergraduate student in the Department of Health Science here at Northeastern and a research assistant in the Movement Neuroscience Lab. I have been fortunate enough to be involved in the ALS project for about a year and a half now, and my intention after graduation is to pursue a career in medicine. My work on this project has greatly inspired me to focus on neuromuscular diseases such as ALS in my career.
Hi, my name is Matt Urasi, and I'm a biomedical engineer and associate research scientist in the Movement Neuroscience Lab. I have over 15 years experience researching neurological disorders such as spinal cord injury and stroke. We will now give you a brief demonstration of how some of the tools and techniques we are using to innovate biomarkers of ALS. Here we are in the Movement Neuroscience Laboratory. As you can see, Natty is holding the transcranial magnetic stimulator, this blue and white box to my right, over the research participant's head. The research participant is seated and performing the task, and Natty has full feedback of what's going on in the experiment in the screens above. The black sensor taped to the research participant's hand is recording the electrical activity of the muscles and the response to stimulation. Her finger is positioned over a force sensor as she completes the task. The research participant is tasked with pressing the force sensor to achieve the target force on the screen. The TMS is triggered when the research participant achieves that force. Here you see our neural navigation system. Natty is holding the coil over the participant's head, and again, each click marks a stimulation. In the bottom right corner, you can see the participant's MRI image. We can co-register that image to be able to precisely target the area of stimulation. On this screen, we're seeing the physiological response to the stimulation. In the top right corner is the EMG activity, the electrical activity of the muscle. Prior to stimulation, we see the voluntary activity. Then we see the stimulation response, followed by a quiet period known as the cortical silent period. That's the measurement of interest for this experiment. In the bottom screen, you see the force exerted by the participant to trigger the stimulator.
Being able to characterize the integrity of the nerve cells in the brain and their connectedness to muscles is paramount to identifying ALS early. But up until recently, neurologists have only been able to measure local signals in the peripheral nerves of the muscle, not the brain. What's more is that this type of test is conducted while the person is at rest, making it hard to detect subtle changes in physiology. By the time those peripheral nerves show abnormality, ALS has dramatically progressed. Imagine, for example, if a cardiologist based her decision on a person's heart health by measuring heart signals while a person is at rest, rather than during a stress test. The test may miss important flags that could only be detected when the heart muscle is being pushed beyond its resting state. By directly measuring the brain and muscles under slightly stressful conditions, we believe that we can detect subtle and early biomarkers of ALS. As you saw in the demonstration, we can use TMS to directly measure the effect of fatigue on neurons in the brain by characterizing the cortical silent period. This period becomes markedly prolonged after a person fatigues, and it can be a sensitive measure at detecting pathological levels of fatigue in the brain. By detecting ALS earlier, potentially before significant clinical signs or symptoms manifest themselves, healthcare providers can begin to implement interventions and support services much sooner than is currently done. Thanks to the generous support of the Cinique Foundation, we hope to have a far-reaching impact on the lives of individuals with ALS as well as their families.